Hi ladies and gentlemen, this is Ms. Skokin. We're back in AP Statistics Chapter 1, Exploring Data or Data Analysis. We're going to be in Section 3 this time, Describing Quantitative Data with Numerical Summaries. We're going to be looking at measures of center, measures of spread, how outliers and extreme values affect measures of center and spread, about determining which is the most appropriate measure of center and spread used to describe different types of data. We're also going to be identifying outliers using a new rule. We're going to be creating box plots and then using box plots and numerical summaries to help us compare distributions of data. You can see our vocab here, and we're going to continue on with a short discussion about measures of center, because again, this is something we've already worked on. Imagine that Mr. McCarthy walked into our classroom and wanted to know how well students did on the last AP Statistics test. What might we use to answer him, to be able to answer his question, and what would that answer actually mean? And in general, when we want to describe a set of number, very often our go-to number is the mean. The mean is not something new to us. We've been using the mean for years and years and years to describe different sets of numbers. So if we wanted to know the height of the 12th grade at our high school, for example, then what we would do is we would measure everyone's height in the group of interest, and that would be the way that we would describe the height of the group. It doesn't capture every individual in the group, but it is one number that we can use to describe the whole group. So let's talk a little bit about mean. And we have different symbols that we use in math, as you know, to be able to get across an idea. And the mean, we have two different symbols that we are going to be using. One of them is going to be what we call X bar, and it's X with a little bar over it. And that is the symbol for when we have a group of data that represents a sample. So it's a subset of a population. And when we are going to describe a population and we want the mean of the population, obviously you can imagine that that is much more difficult to do. For example, if our population is too big to be able to, like all high school seniors in the entire world, for example, it might be very difficult for us to do. So we typically use a sample. We'll talk more about that later, but just so you can see the distinction between maybe taking a sample or a subset of the overall population, such as high school seniors at North Broward versus high school seniors all over the world. Anyhow, when we're dealing with a population, the symbol for mean is a Greek letter that is called mu, and it's pronounced mu. So we know that the formula to calculate the mean is just to add up all the numbers and then divide by the number of numbers. But if we wanted to formalize that, we would show it with the very first formula on your AP Statistics formula sheet that you will be allowed to use on the exam date, and you'll be allowed to use for every test in class also. And this is the formula of the mean. We start out with X bar equals. Every formula has a left-hand side and a right-hand side and the equal sign. So X bar equals the sum of all the individual or independent observations divided by the number of numbers. So we're going to be using N as the sample size, and we know that when we use that Greek letter uppercase sigma, that means to add something together. So the mean can be thought of as the balance point in a set of data. We are going to be talking about that later. We know a little bit about the median, and the median is found by finding the middle number in an ordered set of data. And that's going to be a single value if we have an odd number of pieces of data, or it's going to be the average or the mean between the two middle pieces of data if we have an even number of pieces of data in our data set. All right, let's take a look at an example, and here we have the number of goals scored by the 2016 U.S. women's soccer team in 20 games. So we're going to make a dot plot of the data, and if you remember, we accumulate the dots in nice, perfect, even rows over the appropriate value. So stop the video now to make your dot plot. Okay, we've got our dot plot here, and we can see that the big cluster of data is on the left-hand side from 1 to 5. There aren't no games where they scored 0 goals, so that's of note. The other thing that is of note is we have two numbers way over on the right-hand side where two games, one the team scored 9 goals, the other one the team scored 10 goals. So if we're going to describe the shape of the distribution, the very first thing we need to do is to kind of get an overall look at it. And as we look at it, we do see that data clustered over on the left-hand side. So we would describe it as unimodal and very right skewed, because we do see that big cluster of data on the left-hand side, and not, well, we have a gap at 6, 7, and 8, and then again, just those two games over on the right-hand side. If we want to calculate the mean number of goals scored per game means that we're going to be dividing by 20. That's going to give us an average number or a mean number of goals scored in each of the games. So if we want to show the work, that means we're going to show exactly what our calculation represents, and then we're going to do it in the calculator. I know that it might seem trivial to do this, but sometimes in AP statistics, we're asked to be able to provide evidence or justification for making a statement. And sometimes we're asked to just show our work and show our calculation. And even though we really are going to do the math in the calculator, most of the time, sometimes we do just need to show these simple calculations. So here we are showing the mean, and our mean number of goals scored per game is 3.15. So this is the average. Now the next thing that we want to be able to do is we want to be able to find the median. And in order for us to find the median, we need an ordered set of data, not just the raw data in any order. So it looks like it's chronological the way that it was given to us. So the first thing we need to do is write it down in order. So pause the video now and order the data, please. Here we've got our ordered set of data, and we know in order to find the median, we want, if there are an odd number of pieces of data, we want the middle value. If there are an even number of pieces of data, we want to find the average between the two middle numbers. So the two middle numbers in this case are going to be the 10th and 11th values because we had 20 pieces of data. The two middle pieces of data happen to be 2 and 2. And although we don't officially need to, I'm just going to show you what we would do is find the average of those two numbers and say that that is our median. Now, one of the things that I want to bring to your attention is that these values are very different from one another. And I want you to think about why that might be. But 3.15 as a mean and 2 as a median, if we knew nothing other than those two numbers without knowing the raw data or without looking at the distribution, that would give us some information about the distribution. So let's think about that for a minute, and then we'll continue on. Okay, as we look at that distribution of data, which we see on our dot plot, we decided already that the data is mostly clustered all the way on the left-hand side, but we see these two values all the way on the right-hand side, one game of 9 goals and one game of 10 goals, and we have a sneaking suspicion that these values might be outliers. We don't know, we don't have any evidence, but they definitely don't seem to follow the pattern of the other values. So what we're going to do is we're going to see what the mean would be without those two values. And what this means is we're going to add up all the other numbers, but without the 9 and without the 10. So let's do that now. So again, we set it up showing all of the score values except the 9 and the 10. And what I've done is I've used the ordered set of numbers to be able to calculate the mean this time. And this time we come up with a mean of, and I'm going to round to 3 decimal places. 2.444 is the value that we come up with. and it's actually a 2.4 repeat, but we're not going to show it that way. In AP statistics, we round to 3 decimal places, and that's going to be pretty much all year. Sometimes we might do a little bit more, but we're not going to do less unless we have a value like 2, a nice round integer, or a terminating decimal like 3.15. Anyhow, when we don't include the 9 and the 10, we end up with 2.444 as the mean number of goals scored per game by that 2016 women's soccer team. So think about that. That is a pretty big difference from our 3.15 that we had as the mean previously. So what happens now if we calculate the median the same way? If we leave out those 2 extreme values. Let's give that a try and see what happens. This time we have 18 pieces of data, so it's still an even number. We want the middle 2 values. And somehow the middle 2 values are still 2 and 2, so we find the mean of those 2, and our median is the same number that it was before. That's interesting. I think it's important. So what do we notice? What do we notice about the mean and the median? The mean went from 3.15 to 2.444 without those extreme values, but the median stayed at 2. Now we are going to be talking more about that, but I want you to think about that. Let that kind of percolate or cook, and we will discuss that further. But it is very important, and it kind of guides us into that idea of which would be the most important measurement to use for different types of data. So think about what our data distribution looks like, and think about which number ended up being a better descriptor of that data. All right, let's take a look at how to analyze for a second. We have 2 measures of center that we've talked about so far, and think about what that is. Measure of center means that we want to be able to describe the center of the data. Okay, we have 2 different ways that we can do that. We can do that with the mean, we can do that with the median. And those are the 2 measures of center that we're going to use. And what are some of the characteristics of each one? The mean is sometimes called the fair share measurement, because if we were to distribute whatever the data happens to be, in this case goals, over each of the games equally, then each of the games would have their fair share of goals. And so that's one way to look at the mean. The mean is also very easy to calculate. It's nothing complicated. We add up all the numbers and divide by the number of values that we have. But one of the problems that we have with the mean, and this is pretty important, is that it is affected by the existence of extreme values that we just saw. So it is susceptible to be influenced a lot just because we have 1 or 2 or more possibly extreme values. And they might be outliers, they might not be outliers, but they're outside of the general pattern, so they are extreme values. And that can happen on either side. On the left-hand side, the small numbers, or on the right-hand side, the large numbers. So the mean is not resistant. This is important, and this will push us instead to use the median when we have specific types of distribution. Now notice, I said when we have extreme values, and in general, that is going to happen when we have a skewed distribution, as opposed to a symmetric distribution. So symmetric distributions can come in a lot of shapes and sizes, and it doesn't really matter which one. We know that the mean is still going to give us that center value. And by the way, if we have a symmetric distribution and we decide that the mean is the right measurement, the mean and the median are going to be very close to one another. When we have extreme values, typically that's going to look like a left skewed or a right skewed distribution. And in this case, we know that the median is just the middle value, which doesn't always seem like it would be very useful. But when we have this idea of half the data points above and half the data points below, it does give us a good idea of what's going on in the set of data. And it is also easy to calculate or determine, but the big benefit to using the median, it is resistant to extreme values. And that's one of the reasons that we love to use the median. Now, this doesn't mean that we're not going to use the mean. We are definitely going to use the mean, but we're going to use both of them, and we're going to use them depending on which one is the appropriate one to use. So I want you to just consider for a moment, when we have a skewed distribution and we find that idea of half the numbers are above and half the numbers are below, where do we expect that mean to be? And the mean is going to end up closer to the tail of the distribution. So the median, remember, is always that middle point where half the data is above, half the data is below. Because we know the effect of the non-resistant measurement of the mean is going to be influenced by those extreme values, it's going to be influenced by those extreme values in the direction of the extreme values. So that's where, if we have a right skewed distribution, we're going to see the mean to the right of the median, and if we have a left skewed distribution, we're going to see the mean on the left of the median. Sometimes it's definitely easier to draw it out so that you can see it, but we know that the mean is always going to be on the side of the tail. Okay, let's talk now about measures of spread, and one of the ones that we're going to deal with is the range. We've already talked about that. We've not yet talked about the interquartile range, so let's talk about the interquartile range. To start with, we're going to abbreviate the interquartile range as the IQR. And then I want you to think about what root word we see in there. And we do see quart, which we know means 1/4. So let's expand on that idea for just a little bit. Imagine that we have a set of data and we put it in order, just like we do when we're trying to find the median, and we break the data up into quarters. So my rectangle is the list of ordered data, and I've literally broken it up into quarters. So 1/4 of the data is in each of the little boxes. And what we've done is we've basically created something that is a graphical representation of all of our data. Now, as long as we scale it properly, it's going to give us a lot of information, but think about this. This is 1/4 of our data. We're going to call this first value, well, let me start here. We're going to call that value the median, but what it really is the second quartile, or we can call it Q2, but we're typically going to call it the median. What does that mean? It means that it's the location where we've already got 2/4 of the data, or 50% of the data to the left, 50% of the data to the right. The value to the left, the first quartile, is going to be called Q1, or again, the first quartile. And that means that we've already had 25% of the data. Now you can pretty much guess what this value is going to be, and that's going to be Q3, or the third quartile, and it means 75% of the data is to the left and 25% of the data is to the right. Now, if we have a very small data set, it's a lot less meaningful to look at it this way, but if we have a relatively large data set, hundreds or thousands of pieces of data, this is super meaningful because it really gives us a lot of information about how the distribution of the data looks and helps us out with those extreme values. Now, the interquartile range is actually a calculation. It's just like when we calculate the range, and what we're going to do is we're going to be doing a Q3 minus a Q1, and that is what is our IQR interquartile range. So we're going to find the median, and those are kind of the steps that we're going to take. We're going to start out with find the median. Then after we find the median, we're going to find the median of the lower half of the data and the median of the upper half of the data. And once we've got the median of the upper half and the median of the lower half, what we're going to do is just subtract them. And once again, the difference between those two is our interquartile range. So you can see it's a type of range, but it's not the big range for the entire set of data that we've talked about in the past. So let's go ahead and do that for our set of data that we've been working with. We know that there are 20 values. Let's go back and find our median again. And if you remember, our median was 2. We found the 2 values in the center of our even number of pieces of data and found the average or the mean of those 2. And now what we're going to do is for the lower half and for the upper half, find the center values. On the lower half of the data, we see that our 2 center values are 1 and 1. So that means the Q1 is going to be the average of those 2 numbers, which of course is 1. On the upper half of the data, we see our 2 center values are 4 and 5. So our Q3 is going to be the average of those 2 numbers, and that is 4.5. Now we're not done yet, because remember what we were trying to do to begin with is to find the IQR. So the IQR is going to be the difference between the Q3 and the Q1, which means 4.5 minus 1, or our IQR is 3.5. That represents the middle 50% of our data. So that's going to be the range in the yellow box. Just a quick note, whether we had a dot plot or we had a stem plot, it would be very easy for us to find these values. If we had a histogram, it would be a little bit less easy because we know that the values would be grouped together. So we might be able to find out which bar the median, the Q1, and the Q3 are in, but we wouldn't necessarily know the exact value. But we can find the value with a dot plot or with a stem plot. Okay, we're going to move on and talk a little bit more about these values that we have found and what we can do to graph them. And here we're talking about 5-number summary, box plots, and the 1.5 times IQR rule for outliers. So we're going to start again with our set of 20 soccer games, the number of goals in each, and let's write down the information that we have so far that we know. And what we've already calculated, of course, first of all, we found the median, then we found the Q1 and the Q3, and we knew the IQR was the difference between the two. So we've got, you notice it says 5-number summary. That means we have 3 numbers, we need 2 more. And the 2 that we're interested in adding to this list are the minimum and the maximum. So we're going to add those 2 into our list, and we've got the 5-number summary. This is the 5-number summary. The 5-number summary is used for a couple different things that we're going to do. One of them is going to be the box plot. So we're going to draw a box plot, but the first thing that we always need, of course, when we graph anything is a scale. The minimum value and the maximum value need to be included, so our scale needs to go from 1 to 10. Let's create a scale now. As we said previously, we're always going to label and scale to begin with. So we've done that. We've got our scale, we've got a label explaining what the data is, and the next thing we're going to do is to graph our data. When we create a box plot, we're going to put these 5 numbers in the 5-number summary on our graph. But again, always start with the scale, because otherwise it's really easy to forget, and then our box plot won't have any meaning because it won't show us the distribution of the data. So I'm going to start out with the minimum value, and I'm going to put a dot at the minimum value. I'm going to put another dot at the maximum value. And then I'm going to draw the median. I'm going to draw a line at the median, and a line at the Q1 and another line at the Q3. And then I'm going to join these together. And that is our box. Now, the last part is we're going to join the box to the minimum and maximum, and you can see our Q1 and minimum value are exactly the same, so it's not going to have the same shape as every other box plot, because we would see a left hand, what they call a whisker, as well. So just FYI, so that you know what you're looking at. This is the box, and this is the whisker. Box and whisker plots could have a left-hand whisker and a right-hand whisker, but you can see that this one has only a right-hand whisker. Now, I want you to notice something. We knew that we had kind of that distribution where most of the data was clustered on that left-hand side, and that's exactly what we see when we have this situation. When we have 3/4 of the data all the way on that left-hand side. The only portion of the data that's in this whisker is the last or the upper 25% of the data. So interesting, right? Because it goes from 4 to 10, or from, I guess, 4.5 to 10, I should say. That's representing 25% of the data, and that's why we see that long whisker. So this box and whisker plot clearly tells us, just like the dot plot did, that we have a very right-skewed distribution. You can also see that if we had another box plot using the same scale, like a back-to-back box plot, we would be able to do a comparison of the two distributions very successfully, because it shows us the 5-number summary and where the data is in terms of each of the 4 quartiles. Okay, the next thing that we're going to do is the 1.5 times IQR rule, which we're going to use to find outliers. Obviously, we're going to need the IQR in order to use this rule, and the IQR that we found before, if you remember, was the difference between the Q3 and the Q1, or 3.5. That was the number. Now, what we're going to be doing is we're going to be finding the lower threshold and the upper threshold for finding outliers. To find the lower threshold, what we're going to do is we're going to subtract from the Q1. So it's going to be Q1 minus 1.5 times the IQR. We're going to substitute in, and Q1 in this case is 1 minus 1.5 times the IQR, which is 3.5. And that's going to give us a value of 5.25, and 1 minus 5.25 is negative 4.25. So what this means is any data values below that are going to be outliers on the lower end of the data. We have no values below this on the lower end of the data. Our lowest value or our minimum value is 1. So there are no values below negative 4.25. So what that means is that we have no outliers on the lower end of the data. And when we're looking for outliers, even though we don't suspect that there are any on one side or the other side, we're going to show the work on both sides. So in this case, we have no outliers on the lower end of the data. And the next thing that we're going to do is we're going to look for outliers on the upper end of the data. And we're going to start by finding the upper threshold of the data. And for this, we're going to do Q3 plus 1.5 times IQR. And in this case, our Q3 is 4.5. We know our 1.5 times IQR is 5.25. So that's going to give us 9.75. And this is indicating to us any data points above 9.75 are outliers. And in fact, if we look back at our data, we have two values that were on the high end, 9 and 10. 9 apparently is not an outlier, but 10 is an outlier. So We write down the maximum value 10 is an outlier, and now we're actually going to have to modify our box plot. And we drew a box and whisker plot up above, but in truth, we're not going to be using a regular box plot. We're going to be using what is called a modified box plot. And the modification to the box plot is that we're going to show outliers as outliers. And you'll see exactly what that looks like in a minute. So pause the video and make a new scale for our box plot. Here we've got our scale and our title. Once again, we know that we're never going to make a box plot without them, so that comes first all the time. The next thing that we're going to do is we're going to put our minimum value in. Remember, we put that in with a dot. And our Q1 was at 1 also. Our median was at was at 2. Our Q3 was 4.5, so there's our box. And now once again we're going to make the whisker, but this time we're going to make a special symbol where we know our outlier is. And I'm going to go ahead and use an asterisk. It's a very easy way to indicate the outlier, and it's very noticeable this way. You can also use a dot, but it's less noticeable. And now our maximum value is going to be at the highest value that is not an outlier, and that ended up being 9, if you remember. So I'm going to make a dot at 9, and then I'm going to draw my whisker to our new maximum. Now we recognize 10 is still the maximum, however, it's also an outlier. So in our modified box plot, we indicate the outlier. And guess what? Your calculator will do this for you. So we'll learn how to do that in class. For right now, we are going to move on. Now here we're going to be looking at standard deviation. So we're going to use, I wanted to use a smaller data set, you'll see why in a minute. And this time we're using only, let's see, I think it's 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces of data. So a group of elementary school children was asked how many pets they have. Here are their responses, arranged from lowest to highest. Smallest number is 1, largest number is 9. I hope those are all fish because that is a lot of pets. The very first thing we're going to do is we're going to calculate the mean. So find the mean number of pets. We find that the mean number of pets in this group is 5. We added up all the values and we divided by the number of numbers, which is 9. And I'm just going to make a note here, n, or our sample size, is 9. So that's how large the group is. Okay, what we're going to do now is we're going to write down the different observations in our table. We're going to do this in a table now, the first time, so you understand the definition of standard deviation, but we're not typically going to do it this way. We're typically going to do it in the calculator. So let's go ahead and write down the number of observations, or the observations, the values in our data set. And the next thing that we're going to do is we're going to find the deviation from the mean. And that means that we're going to find the difference between each individual point of data and the mean. This is why we found the mean first. So in each one of these cases, remember X bar is the symbol for our mean. In each one of these cases, we're going to find the difference with the mean. So all of these are going to be subtracting 5. And now I'm going to put the observation in. And then we're actually going to find the differences. The first difference is -4. Once we've got the table filled in, the next thing that I want you to do, just so that you can see what's going on here, is add up this column of deviations. And you can see that our sum is, if you add up all of these numbers, our sum is 0. Now, what does this mean? Standard deviation, what we're trying to do is we're trying to find the average difference from the mean. But when we find the average difference, we end up with 0. 0 divided by 9 is going to still be 0. So finding the average difference from the mean can't be as simple as finding all of the deviations and then finding the average, because the deviations are always going to add up to 0. So what we do instead is we square the deviations. And we know when we have a negative number or a positive number, when we square them, we end up with a positive number every single time. So we're going to fill out the squared deviations in the table. And then we're going to add those numbers together. When we add these numbers together, we get 52. I'm going to detour here and just remind you that when we found the mean, we found the mean of a sample is going to be x bar, and the mean of a population is going to be mu. We have a similar situation when we're finding standard deviation. For standard deviation, we're going to have different actual calculations. And when we're dealing with a sample, we're going to divide by n minus 1. When we're finding the standard deviation of a sample, we're going to divide by n. So what that means is we're going to take this number 52. We know that the 9 elementary school children was just a sample. That was not all elementary school children in the whole world. So we're going to take our number that we found, 52, and we're going to divide by n minus 1. So our sample size, 9 minus 1. And the value that we get is 6.5 pets. But it's not really pets because we squared all of our deviations. So the units are pets squared, which is just weird. Anyhow, that is called the variance. This number is called the variance. But that's not what we set out to do. If you remember, we said that we were looking for a standard deviation, and that is what we're interested in. So we're going to take the square root. So the square root of 6.5 is approximately 2.55. Now our square pets are just pets again, and this is our standard deviation. So we found our standard deviation, which is what our goal was. Now the last thing that I want to do is I want to write down the formula for standard deviation. So it's basically going to be exactly what we did. And in this case, we don't have a standard symbol for standard deviation like we do for some things. So the symbol that we're going to use is either going to be, if we're dealing with a population, it's going to be sigma, and that's lowercase sigma, or if we're dealing with a sample, we're usually going to use S sub x, or S for standard deviation with a subscript of x. We know that sigma is the Greek letter S, so we're going to use that. Anyhow, our formula for standard deviation is exactly what we did. The sum of all the squared deviations divided by 1 minus the sample size. This formula is also on your AP Statistics formula sheet that you'll be allowed to use on every test and on the exam. However, we usually let our calculator do it. So this brings us to just some basic points that I want to remind you of. Now notice, because we square and square root, the standard deviation is always going to be positive. We're going to write down these notes. But first, let's just write down what the 2.55 represents. On average, the number of pets the school children have is 2.55 from the mean, 2.55 different from the mean, on average. That could be above, that could be below. But what this does is this gives us a measurement of how spread out the data is. But it's spread about or around the mean specifically. So we used the mean to calculate standard deviation, and then it gives us an average difference from the mean. So standard deviation and the mean go hand in hand. The next thing that we need to note is that standard deviation, remember we squared and then square rooted, so standard deviation is always positive. How could we have a standard deviation that is equal to 0? Well, the only way that that could happen is if every point in our data, and I should do this really, every point in our data is actually equal to each other. So if there's only one value amongst all of the different pieces of data, and then we find the standard deviation in that case would be equal to 0, because the independent or individual value minus the mean would be 0 every time, and when we square it, it would still be 0. So standard deviation is really always going to be positive unless there is no variability in the data, and that would be the only case in which it's equal to 0. Obviously, it can never be negative. And the more spread around, or the larger the differences from the mean in the data, the larger our measurement of standard deviation is going to be, telling us once again how spread out is the data around the mean. The next important idea is that the standard deviation is always in the same measure or same units as the original data, because we took the data, we found the difference from the mean, that kept the units the same, then we squared the differences, now we have square units, but then we took the square root, or we divided and then we took the square root, so we're back to the original units. And last of all, we need to remember that because we calculated the standard deviation from the mean, like the mean, the standard deviation is not resistant to extreme values. So think about what that means with what type of data we're going to use standard deviation for and mean for. So just like we saw median and interquartile range and the 5-number summary, those all go together. Mean and standard deviation go together. All right, let's take a look at the next page, and this is an activity that we're going to do in class. So the video stops now. We're going to do this in class when we get together again, and then we'll be working on practice problems after that. See you in class.